Yeah, hi. Not sure what it means to be a rock star, whether like I trash hotel rooms or something like that. Anyway, so, well, yeah, welcome to my talk on asynchronous microservices. And really what the goal of the talk is to describe how to implement transactions and queries in a microservice architecture using asynchronous messaging. And as you're going to see, there's sort of some kind of essential characteristics of the microservice architecture that make it slightly challenging to do transactions and queries. And then along the way, I'm going to sort of describe why there's more to microservices than just REST, why there's more to microservices than just events. And microservices don't have to be implemented with event sourcing. And also going to just throw in there that, contrary to what's sort of written on various websites, Apache Kafka is not really an event store. It's an excellent message broker, but it's only part of a solution for implementing event sourcing. Anyway, before I talk about that, a little bit about me. I've done a number of things over the years. Way back, did Lisp, wrote the book POJOs in Action. That was 12 years ago. Then discovered Amazon EC2, created the original Cloud Foundry that was a PaaS for deploying Java applications on EC2. Anyway, that's sort of more ancient history. For the past 5 years, I've been pretty much focused on the microservice architecture. So I do kind of basically travel the world doing consulting and training and just generally helping organizations adopt the microservice architecture. And I also have the site microservices.io, which I'm sure many of you have read. And I also have a startup. We're building a platform to simplify the development of business applications that use microservices. And yeah, my book, Microservices Patterns, just came out earlier this month. And you can buy it from the Manning website with a discount code CTW YOW Conf 18. And I will repeat that at the end of the conference, end of the talk. In terms of what I'm going to talk about, first I'm going to describe the problems that you have implementing transactions and queries in a microservice architecture. Then I'm going to describe how you go about implementing transactions using a mechanism known as sagas. I'm going to describe how you can implement queries using an event-driven approach known as CQRS. And then I'm going to finish up by talking about what I call transactional mechanism, which is basically a way of publishing events as part of a database transaction, which is non-trivial, even though on the surface it seems quite straightforward. Okay, so let's get going. So, first off, well, what is the microservice architecture? Well, it's an architectural style that structures an application as a set of loosely coupled services. And they're generally organized around business functions. And one of the key things there is loosely coupled. And that actually means that microservices can't share databases, or to be more precise, they can't share database tables. I'm going to talk more about that in a minute. An individual service, from the perspective of its clients, is defined entirely by its API. And the API of a service consists of two parts. The first part are its operations, which are things that you can invoke. And there's two types of operations. There are commands that mutate data, so create order, cancel order, revise order. There are also queries that retrieve data. And these operations can be invoked either synchronously, using something like REST or gRPC, some synchronous protocol like that. Or, as you're going to see in this talk, they can also be invoked asynchronously by sending what's known as a command message. And in some situations, that's kind of a key mechanism that you need to use in order to maintain data consistency. And then the other part of an API of a service is that it publishes events. Or to be more precise, DDD, domain-driven design, domain events. So like order created, order revised, order canceled, order shipped, and so on. And that's sort of another kind of key mechanism that you often end up using. So from the perspective of a client, that a service is defined by its innate API. Now, in terms of its implementation, a service can invoke the operations of other services, And as you're going to see, it can also subscribe to their events. And then, of course, a service has a database where it's storing its data. It also might have a replica of data that's owned by other services. So this is the basic building block of a system that has a microservice architecture. And the reason you want to use this architecture is first and foremost to tackle complexity and to enable you to do rapid, frequent, and reliable delivery. In other words, DevOps of large, complex applications. So this is generally not an architecture that you'd want to use if you have a small application and a small team. But once your application gets large, as successful applications inevitably do, and your team gets large, this is an architecture that you want to consider. And the reason you would want to use this architecture is that it gives you the deployability that is needed to support DevOps. These services can be developed and tested and deployed and scaled independently of one another. And this architecture also gives you the testability. One of the key sort of foundational techniques of DevOps or continuous delivery is automated testing. And in order to do automated testing, you need an architecture that is testable. And the microservice architecture is exactly that. And then the second way in which microservices support DevOps is because it enables you to have loosely coupled autonomous teams. So you've got loosely coupled services that are owned by loosely coupled teams that can develop, test, and deploy their services independently. So this is the primary reason why you want to use the microservice architecture. And there are other reasons, like it can help with scaling and so on. But first and foremost, it's to tackle complexity and to modularize your application. So let's sort of look at a simple example. So imagine that you're building an online store. So that application will have APIs for creating customers, creating orders, and doing queries, retrieving customers, retrieving orders, and so on. So that from the outside, it's going to implement that API. Now, internally, you could imagine that it will have a customer service that's responsible for all of the operations on a customer. It would also have an order service that's responsible for all operations on an order. Now, each one of those services will have its own database. This is one of the essential characteristics of the microservice architecture. In order to ensure that these services are loosely coupled, they cannot share database tables. If you're working on the order service, you want to be able to quickly and easily change its schema without having to coordinate meetings with or schedule meetings with the 10 other teams whose services are also accessing your services database. That will just slow you down. So for that reason, the data that is owned by a service is encapsulated by the API and is only accessible through that API. Okay, so that's actually the source of the problems that you run into around transaction management and querying. And then sitting in front of your services, you'd have an API gateway that routes requests to operate on customers to the customer service, routes requests that operate on orders to the order service. And sort of, at that level, it all looks quite straightforward. But there's a couple of interesting problems. Sort of the way it's drawn here, the two services are somewhat sort of independent of one another. But if you look at the meaning of the create order operation, it actually has to ensure that there's sufficient credit available for that customer in order to place an order. So in other words, you need a transaction that spans the order service and the customer service. And then there are query operations that retrieve data from both of those services. And doing those things are quite challenging. So for instance, if you think about enforcing the credit limit, in a monolithic system, that's quite straightforward. You simply begin an ACID transaction, you find the existing orders, you retrieve the customer, you make sure there's enough credit available, and then you create the order and you commit the transaction. And the great thing here is that the isolation property of ACID transactions ensure that even if there are simultaneous attempts to create orders for the same customer, the credit limit will be enforced at all times. But even a simple transaction like this cannot be implemented directly in a microservice architecture because orders and customers are actually in two separate services, so you can't access them within the same transaction. Because if you did, you'd actually need to have a form of, you'd need to use a distributed transaction two-phase commit or XA. And that's just a technology that's not used in modern applications. For one reason is it impacts availability. Another reason is that it is not supported by many modern database technologies. So it's sort of like, well, if we can't write transactions like in the usual way to maintain data consistency, well, what are we going to do? And then we also have a similar problem with queries. You know, it's extremely common to just do joins between tables. You know, you want to know about customers and the orders, well, you just do a join between those tables and retrieve the data that you need. But once again, customers are in one service, orders are in another service, and you cannot do a straightforward join between tables. So we've got two problems, how to implement transactions and how to implement queries. So we look at the problem of transactions first. The solution there is to use a mechanism known as sagas. And the idea of a saga, you know, it's sort of kind of a long, I suppose if you think about the kind of the everyday meaning, it's sort of like a long story, right? So it's actually an old idea. It comes from a paper that was that was published back in 1987. And so the idea of a saga is instead of a distributed transaction or a long transaction that spans multiple services, you use a saga that is a series of local transactions, you know, one in service A, another in service B, and a third in service C, and so on. And as you're going to see, those individual local transactions are coordinated through some form of asynchronous messaging. And in the case of the create order saga, it would work like this. Request comes in to create an order. The order service would create that order, and it's in a pending state, which indicates that it's in the process of being created. You know, we actually need to go off and validate reserve credit, and if there was inventory involved, we'd have to go and reserve inventory and so on, so forth. Then the next step is to go and reserve credit in the customer service, and assuming that that's successful, the final step is to go and approve the order back in the order service. So instead of one distributed transaction, we have a series of local transactions, which in some cases is extremely simple to implement, but there are a number of sort of challenges with implementing sort of data or managing data consistency in this way. So the first issue you run into is API design. You basically could have a REST call, you know, a synchronous REST request like create order, poster/orders. Now it's initiating what is basically an asynchronous operation. And so there's an issue of, well, when do you send back a response? Do you wait until until that saga is completed, which would actually impact availability, or do you return immediately once you've initiated the saga, which means that you can't tell the client the outcome of the operation. You can just say, I've received the request to create an order and I'm working on it, which is actually the preferred approach, but it pushes the burden of continually checking the status of the order back to the client. Or you can send them an event, but it complicates your API design. The other problem you run into is, if you look at ACID transactions, you can perform an arbitrary number of updates and then execute a rollback statement, and it's as if those updates were never performed. With sagas, each step is a local transaction that commits its changes, and so you no longer have automatic rollback. You actually have to design and implement compensating transactions that explicitly undo what was done previously. So that's a complication. And then the third complication is that sagas are ACD. They're not actually isolated from one another in the sense that ACID transactions are isolated. So the execution of sagas can be interleaved, and they can basically, you can essentially access data. One saga can access data that is currently being updated by another saga, which can result in sort of data anomalies. And that ends up requiring the use of countermeasures. Which I've talked about in detail before. That's sort of a whole other presentation. But you've already seen an example of a countermeasure. Where in the example, when an order was created, it was in a pending state. That's an example of a semantic lock, which indicates to other sagas or other transactions that that order is in flux and it's still being worked on, and to either not attempt to change it or to kind of take its state, be cautious when observing its state. And it turns out that this all sounds rather complicated, but in general, in many cases, it's actually quite straightforward to implement. So that's sort of the basic idea. You break up what would otherwise be a distributed transaction into a series of local steps. So then that sort of raises the question, how do the participants of a saga collaborate? And you might think, well, we'll just use REST. And in some cases, that might work, but there's a whole bunch of issues. Number one, REST is a synchronous protocol that requires the client and the server to be available during the request, so that introduces temporal coupling. And then the other issue you run into is how to recover from failure. So the customer service could fail. That's a simple recovery because the order service could just keep retrying until it succeeds, assuming that the reserve credit operation is idempotent. But then, well, what happens if the order service fails? Then the system is sort of in this really weird, inconsistent state, and it would rely on the client to actually continually to keep retrying the create order operation until it succeeds, which can work in some situations, except that you're sort of relying on a client that is outside of your firewall to ensure that the data inside your system is consistent. And as you know, users can just close their browser, walk away, go off for lunch, and so that doesn't feel quite right to me. So it turns out that a much better way to ensure data consistency and to reliably implement sagas is to use asynchronous messaging. So the participants in this saga are exchanging, communicating via a message broker. So the order service will execute its local transaction, send a message via the message broker to the customer service, and so on and so forth. And this will actually ensure that the saga completes. You use a message broker that gives you at least once delivery. So that means that if the order service performs one step and publishes a message, the message broker will keep trying to deliver that message to the customer service, and deal with handle the scenario where the customer service is temporarily unavailable. And so this means that once the saga has started, it is guaranteed to complete, even if some participants are temporarily unavailable. And you also want a message broker that gives you order delivery, and you want a message broker that lets you scale out consumers while preserving ordering, which requires, if you look at modern brokers like Apache Kafka, they have this feature. Older ones like ActiveMQ do as well. RabbitMQ, not so much. You end up having to implement a whole kind of complex mechanism to scale up RabbitMQ in this way. So that's the idea. The participants communicate via a message broker that gives you ordered at least once delivery. So then that means that each step of a saga does two things. It updates the database, creates an order, reserves credit, approves an order, and it publishes a message or sends an event. And interestingly, there's sort of a sub-problem here, how to ensure that both of those things happen atomically. In a traditional application, you'd use like the Java Transaction API, JTA, to have a distributed transaction spanning your database and your message broker. But that's not something we want to use here. And later on, I'll describe the mechanism. There's a couple of different ways of ensuring atomicity without using two-phase commit. And then the next question is, well, how do we actually coordinate and sequence the series of local transactions? So when one transaction finishes, a message needs to be sent to the next participant. So we need some logic to decide, based on the outcome of the local transaction, who to invoke next. And there's two possible coordination mechanisms that you can use. One is choreography, where the decision-making is distributed amongst the participants. And then the other one is orchestration, where the decision-making is centralized in basically a workflow or a state machine, or an object that implements a state machine. So if we look at choreography, it's actually quite simple. So the participants just exchange messages. As you're going to see, the order service publishes messages which get consumed by the customer service, and vice versa. So in the case of the create order saga, request comes in to create an order. It actually creates the order, and it publishes an order created event. Then that event gets consumed by the customer service, which will then attempt to reserve credit for that order, and then based on the outcome, will publish an event, either a credit reserved event indicating success, or a credit limit exceeded event indicating, well, I tried to reserve credit, but there wasn't any available. The order service then will receive one of those events and then either approve or reject the order. So we just have a bunch of events bouncing back and forth between the services, and eventually your system is in a consistent state. The order is created, and the credit has been reserved. So it's a fairly simple mechanism, and in lots of simple scenarios, it actually works extremely well, and it's quite easy to use, especially if you're implementing your business logic using a pattern known as event sourcing, which I'll describe in a little while. It also means that the participants are loosely coupled. They're just communicating asynchronously using these events. There's no temporal coupling between them. But there are a whole bunch of downsides. So number one, the coordination is decentralized. You can't look at a single piece of code and see how the create order saga is implemented. You actually have to look at a whole bunch of event handlers and business logic that's publishing events and consuming events. There's also cyclic dependencies. These services are listening to each other's events, which seems sort of a bit of a design smell. And then not only that, the customer service has to know about all of the order events that could possibly impact the available credit, which sort of means that it's having to know a little bit too much about the order service, which doesn't seem quite right. And then sometimes when you're implementing sagas, you just want to tell one of the services to do something. But with this approach, you can only publish a sort of, you can announce what you've done, and you can't tell what someone else needs to do. It's sort of a passive-aggressive kind of style of communication. But as I said, sometimes this works extremely well. And if you want to look at a code example, I have quite a few online. So the other option is to use orchestration, and that's simply where you have a sort of orchestration object that tells the participants what to do. As you're going to see, the customer service is told to reserve credit, and then the order service is told to approve the order. So instead of a service just saying, well, I've done this, now the participants are being told what to do. And so this orchestrator is a persistent object. In some ways, it's almost like another domain object or a DDD aggregate. And it implements a state machine. And its sole responsibility is to tell the participants what to do or receive replies from them and then figure out what to do next. So when one of these orchestrators is created, it basically sends a command message, as you're going to see, to a participant, and then gets saved in the database, waiting for a reply to come back. And you can imagine the command message has a header that contains the Saga ID that gets returned in the reply. So when the reply comes back, the framework will retrieve the Saga instance from the database, hand it the reply. The Saga orchestrator then determines what to do next, which participant to send a command message to, and does it, updates its state, undergoes a state transition, in other words, and then it gets saved in the database waiting for a reply to come back. And it just keeps going around this cycle until it reaches an end state. So in the case of the create order Saga, it would work like this. Request comes into the order service. The order service, actually in this design, it creates the order first and then creates the create order Saga. Now, in a different design, they could be combined, and that could be combined into one step. So it's sort of using the create order Saga to finalize the creation of the order. So the first thing the create order Saga does is send a reserve credit command message to the order service. So instead of pub-sub event-based communication, this is one-to-one sending a command message to a particular service telling it to do something. Customer service will process that command, reserve credit, and then send back a reply message which contains the outcome of that operation. That gets, in this case, the credit was reserved. This gets consumed by the Saga orchestrator, which then approves the order. So at a high level, if you just kind of squinted at this, there's like services communicating via message channels, but the style of communication is very different. Instead of events, it's actually command messages, which are invoking commands asynchronously on some other service. So, this is quite a good pattern. It's a little bit more complex than choreography, but it does have some benefits. First, the actual coordination is centralized in one piece of code. If you go look at the code example, there is a class that implements this create order Saga, and you can see the individual steps. It also reduces the coupling between the services because the customer service is simply told to reserve credit, release credit. It no longer has to know about all of the order lifecycle events. It's just focused on doing customer things, which is exactly what you want. And it gets rid of cyclic dependencies. Now, there is a risk that you could overload the Saga with too much business logic. And so that's something you just want to look out for and avoid. You want to push the business logic down into the Saga participants. That's orchestration. So my preference is you could use choreography for really simple sagas, but once it gets a little more complex, you really want to consider using orchestration. So that's transaction management, which is the much more complex topic. And now I want to spend a little bit of time talking about queries. So, queries in a microservice architecture often retrieve data that's owned by multiple services. So you can imagine in this online store, the client can execute queries that retrieves customer information and order information. So there's one simple pattern that you can use is API composition. And what happens there is the API gateway implements that query, by simply retrieving the data from the services that own the data. So in this example, it's finding the orders for a given customer. So it just goes and gets the customer information from the customer service, and then goes and retrieves the orders for that customer from the order service, kind of combines the data and returns it. Quite straightforward. And whenever you can, you should use this pattern. It's just that you'll often encounter a query that cannot be implemented efficiently using API composition. So here's a slightly more complex query which finds recently created customers that have placed orders over a certain amount that have been shipped. Now, in a monolithic system, that's trivial. You just do a join with the appropriate where clause, and you're done. And in a microservice architecture, you could try and implement that using API composition, but it would be pretty inefficient. So, for instance, one way to do it is you ask the customer service for all of the recent customers. That gives you back a list of customers, and then you iterate through that list, invoking the order service, asking it for its high-value orders for that particular customer. Kind of simple, but that could exhibit really high latency because of lots of round trips. Basically, it's an n+1 query. The other option is you ask the customer service for all of the recently created customers, you ask the order service for all of the recently created orders, and basically do an in-memory join of those two data sets. So that's kind of good in the sense that it's just 2 round trips. It's just that each of those queries could give you back a large amount of data that you then have to join together in memory. So that could be also quite inefficient, and you could imagine other scenarios where that gets, basically you end up implementing a distributed query engine, which is really not the best use of your time. So that's sort of the issue with API composition, is that there are a lot of scenarios where it really doesn't it's just too difficult to implement it that way. So the solution for these queries is to use the pattern known as CQRS. Basically, it's a sort of a command query responsibility segregation, which is a very complicated way of saying simply maintain a replica of the data in a format that makes it easy to query. So for a given query or for a given group of queries, you design a database schema using whatever database technology makes sense for those queries. Like you might use Elasticsearch or MongoDB. Depends on the nature of those queries. And what makes it interesting is that view is kept up to date by subscribing to events that are being published by the order service, or by the services that own the data. So in this example, the customer order view service subscribes to events from the order service and subscribes to events from the customer service. And when it receives those events, it's updating its replica. So a very simple idea. In fact, people have been using this sort of pattern for a long time. It's very common to use MySQL or a relational database as your system of record, and then copy the data into Elasticsearch or Solr so that you can do text searches against it. That, in a sense, is a simple form of CQRS. The one difference, perhaps, is that the view with CQRS, the view is kept up to date in near real time by subscribing to events rather than periodically doing ETLs against the system of record. So in the case of orders and customers, you could, for instance, use MongoDB. Here's one of the examples I have where a MongoDB document is basically a JSON object. There's one MongoDB document for each customer. It has information about the customer, their name, their credit limit, etc. And it has information about their orders. So the customer information is kept up to date by subscribing to customer events. The order information is kept up to date by subscribing to the order event. And the nice thing about this is that Mongo is storing this, what is in essence a pre-joined blob of JSON. So with one simple primary key query, you can retrieve all this information about a customer and their orders and return it to the client that's requesting the data. So very efficient, very scalable. So the origin of the name CQRS, or Command Query Responsibility Segregation, comes from the fact that in a traditional application you're supporting, but you have commands which are mutating data, you have queries that are retrieving data, and normally there is a single data model, single schema that's supporting both commands and queries. And with CQRS, the idea is that you're segregating them. So you have one data model for the commands and another data model for the queries. And the query side data model is just kept up to date by subscribing to the events that are being emitted by the command side whenever data, or more specifically, DDD aggregates are being created, updated, or deleted. And at an architectural level, you could very well have multiple of these query side views. The idea is for each group of queries, you define a schema that will support that group of queries efficiently. So for instance, if you've got, you need to return blobs of JSON to a through a REST API, you could use MongoDB. Whereas if you need to do text search queries, you can do Elasticsearch. And then if you're doing graph queries, maybe this is finance and you're doing fraud detection based on a graph of customers and accounts and transactions, you would dump the data into a graph database like Neo4j, which efficiently implements graph queries. And if you wanted to run a traditional report writer, BI tool, you could even use a SQL database as one of these views. So, it's kind of, you just basically have as many views as you need to support each group of queries efficiently and with good scalability. Now, one interesting thing is that these views are actually disposable. If you suddenly decide, oh, this query needs to return an additional attribute that was not previously being stored by the view, you can actually just go and rebuild these views from the source of truth. If you're using event sourcing that I'll talk about later, you conceptually replay all events from the beginning of time and rebuild the views. If you're using traditional persistence, you basically do an ETL out of all of the source of truth databases to reconstruct this view, and then use events going forward to keep it up to date. So that's quite nice. And then one issue that you can run into is replication lag. There will be a delay from updating the command side to that view being updated because, well, an event gets published, has to flow through the message broker, get processed by the query side event handler to update the view. That's analogous to querying from a MySQL slave. There's always this replication lag. And so as a result, there's the possibility that you could show stale data to the user. Like a naively implemented API UI could do an update and then immediately turn around and query the query side and show the old version of the data to the user, which would be pretty confusing. So as a UI developer, you actually have to do some work to hide this lag from the customer, from the user. So for instance, update the browser-side data model, if you're using Angular or React, and so as to avoid having to go and query the query side. And with the idea that by the time the user ever triggers a query, the query side is up to date. And interestingly, if you look carefully at a lot of complex UIs, you often see hints of sort of replication lag. I've seen it in banks and other places. Anyway, so that's CQRS. Now, in the remaining few minutes, I just want to talk about transactional messaging, which is a mechanism that's sort of underpinning sagas and underpinning CQRS. So if you think about sort of the fundamental kind of sequence of operations, with sagas, it's like each step of a saga has to update the database and publish a message or send an event. And likewise, if you're using CQRS, whenever the command side data model is updated, you need to publish an event. Now, it turns out that in order for your system to be reliable, both of those things have to happen. If you update the data and fail to publish an event, your system is in an inconsistent state. If you update data, commit the transaction, crash before publishing the event, you've got an inconsistency. Alternatively, if in the middle of a transaction you publish a message and then the transaction gets rolled back, you have a similar kind of inconsistency. You've told people that you've changed data when in fact you haven't. So there's sort of this really interesting challenge, which is even more challenging to solve because you cannot use two-phase commit. So one solution that can work in some scenarios is to just simply publish to the message broker and then have an event handler that updates the database. So this guarantees atomicity, right? The publishing and the update are guaranteed to happen eventually. But it does mean that a service cannot read its own writes because the writes don't happen immediately. You've got a very eventually consistent data model, which makes it basically impossible to write common forms of business logic that need to do a read to verify certain preconditions and then do an update. So you end up having to use sort of a more elaborate mechanism. This will work in some very simple scenarios, but doesn't really work in most sort of typical business, enterprise application business logic. So one option is to use a mechanism known as event sourcing, which is an event-centric approach to writing business logic and doing persistence. So your business logic is written just solely to generate events. And then when it comes to persistence, it takes an absolutely fascinating approach. Basically, every one of your business objects, or to be more precise, DDD aggregates, is persisted as a sequence of events. So in other words, there's no order table in your database, there's no customer table. Basically, there is an event table that stores the events. So when you create an order, you insert an event into that table. When you approve the order, you insert an order approved event. And when you ship an order, you insert an order shipped event. And this is the system of sort of the source of truth as to the state of your order. When you want to recreate that order in memory, you query the database, you get the series of events, and you replay them. You can imagine there's an apply method on the domain object that takes an event and updates its state. This is very easy to think about in the context of a bank account where you've got credit and debit events that just adjust the current balance. So the key thing here is, in order to use this, you need to retrieve events by the ID of the aggregate, which kind of means that just using a message broker like Kafka is not sufficient to implement an event store. You actually need the database part in addition to the messaging component. Now, you can certainly use Kafka for the messaging component because the other key aspect of an event store, which is why it's really relevant, is that the events that are inserted into the event store can be subscribed to. So the customer service can subscribe to the stream of order events, and the order service can subscribe to the stream of customer events. So this gives you one way of reliably, sort of one of the guarantees that the event store gives you is every event that is inserted into the event store will be published. So this is one mechanism that gives you the atomicity that you need. And essentially, instead of having separate state and events, there's just events. So it solves the atomicity problem that way. Plus, there are these sort of other useful, other benefits of event sourcing. Namely, it preserves the history of domain objects, so you can do temporal queries. You can actually go back in time to figure out how to retroactively fix things, which can be useful. And you get guaranteed ordering. Auditing as well. The event can store the ID of the user that made the update. But there is a whole bunch of downsides with event sourcing. It's a very unfamiliar programming model. The events conceptually live forever, so you have to deal with the challenge of schema evolution and supporting all the old versions of the schemas from the beginning of time. The event store only supports primary key-based lookup, so it forces you to use CQRS. And then in terms of sagas, it actually does a really good job of supporting choreography because event sourcing just generates the events that drive a choreography-based saga. But it's not such a good fit for orchestration because it's generating events, and we need to translate them into those events into reply messages. And so there's an extra translation step that you need to implement. So anyway, it's kind of an interesting approach. The other option is simply to use traditional persistence. So when you migrate to a microservice architecture, you can just use your traditional persistence framework. So in the Java world, JPA, my bad, is Hibernate, so on and so forth. But then you have to, in order to get the atomicity of messaging, you have to use the transactional outbox pattern. So what that means is you write sort of normal code like this that saves your, in this case, the order in the database, and then publishes the domain event. So that sort of looks kind of straightforward. But what's actually happening under the covers is the domain event publisher is not directly publishing to the message broker, but it's inserting a message into a message table that's basically functioning as the outbox for that service. And that's done as part of the ACID transaction that's updating the order or updating the customer. So we get, we have an ACID guarantee at this point. When the transaction commits, a message will be in the outbox. The question you have is then how do you get the message out of the outbox, the message table, to the message broker? So the preferred way is to actually tail the database transaction log or commit log. Every committed change ends up by definition, ends up in the transaction log and commit log. And so how you do that depends on the particular database, so MySQL bin log, Postgres write-ahead log, or so on. So the actual mechanism is very database specific, but there's frameworks, including the one I've written, that just takes care of that. The other option, which is very generic, is just simply to periodically execute a query against the database that finds the messages that haven't been published, publishes them, and then marks them as having been published. But that can introduce issues around latency. Anyway, so you've got two mechanisms. As I said, the preferred one is to tail the transaction log, and that's an approach which is becoming increasingly common. So that's my talk. So in summary, right, asynchronous messaging plays a key role in solving the distributed data management problems in a microservice architecture. Services will typically publish events either to implement choreography-based sagas or to implement CQRS. Services can also exchange command reply messages to implement orchestration-based sagas. And then you need some mechanism to atomically update state and exchange messages, whether that's event sourcing or the transactional outbox pattern. So that's my talk. Thank you for listening. Hope that you found it useful. And if, I'd love to get feedback, so please ping me, shoot me an email. And also, consider buying my book, 40% off, today only. Thank you.